This is 40 Days of Chemistry, part 28, special for 2014, this time looking at electrolysis calculations in particular. This first slide is just a recap of the other 9.6.3 slide, reminding you the differences between galvanic and electrolytic. This is something you can copy down and look at in your own time if you wish, so you can always pause the video. But the main idea is that spontaneous versus non-spontaneous, you produce a current and voltage with galvanic, but you supply a voltage and current with electrolytic. The anode is negative, the cathode is positive in galvanic, and it's the opposite in electrolytic. Usually we draw galvanic cells as the two separate electrolytes joined by a salt bridge with two separate electrodes. Just be aware you can have the galvanic cell happening in the one electrode, as shown in this example here, but usually we draw electrolytic cells all in the same electrode. They've got a lot of things in common, these things are their things in common. These are just the steps to actually performing a electrolysis calculation. We're going to go through the steps and show examples. We're not going to linger very long here, but if you want to pause this slide and copy stuff down, you're more than welcome again. Once again, this is in the other video as well. Just a reminder that there's three things that affect what reaction actually takes place in electrolysis. First of all, change electrode material and you may change the electrolysis reaction. Change the electrolyte and you're pretty much guaranteed to change the electrolysis reaction, or you can change electrolyte concentration, because sometimes at high concentrations the E0 values change enough that you might get different reactions happening at the electrodes. So let's look at some examples to actually show these things. But once again, if you want to write this down and get some notes, you can always pause this video. The first example we're going to look at is we're going to do electrolysis of aqueous potassium bromide, which you can see here, using inert, in this case platinum electrodes, which means the electrodes themselves are conductors, but they do not react. There was a question at HSC a while ago saying why we use graphite in electrolysis reactions. Well, graphite's cheap, but the main reasons is that graphite's inert, it's not going to take part in the redox reactions, and also it's a conductor. You need to be able to supply electrons or remove electrons. It needs to be a conductor to be an electrode. So when you're doing electrolysis, the first thing you do is look at the cathode. And we know that at the cathode you have reduction, and from oil rig, reduction is gain. So you need to ask yourself what sort of things could possibly gain electrons. Now, non-metals we know react by gaining electrons or reducing. Cations, they're already positively charged, that means they can accept electrons, so they can be reduced, and neutral compounds can be reduced. So looking at our cathode here, we've got to ask what chemicals are here, first of all. So here's the chemicals we have at the cathode. We've got platinum, obviously, we've got potassium ions, bromide ions, and water, but some of these won't take part in the reduction reaction. And first of all, we know platinum's inert, it won't take part in reduction. Bromide ions are already negative, they will not accept any more electrons. So we've got to ask ourselves, make the decision, what is going to be reduced out of the potassium ions and the water? And this is where we go, the most positive reduction potential is the one that's actually going to be reduced, or you could go via anodes before cathodes and look down your list. The lowest one on the list is obviously going to be your cathode. And looking at your list of standard reduction potentials, here are the two reduction equations. Potassium ions being reduced has an E0 reduction of minus 2.94 volts, whereas water being reduced to turn into hydrogen gas and hydroxide ions has an E0 reduction of minus 0.83. So minus 0.83 is the more positive value here. And that means this is the one that is actually going to be reduced. This is the reaction that will actually happen, and this one will not happen. The next thing we've got to look at is now the anode. Now we know the anode is where oxidation occurs, and oxidation is a loss of electrons. So what can lose electrons? Typically only metals. We know metals react by oxidation, so metals lose electrons. Anions have a negative charge, that means they can lose electrons, and neutral compounds can lose electrons too. So looking at the species we actually have at the anode, once again we know platinum, it won't undertake reaction, therefore it won't be oxidized. The potassium ions have already lost an electron, they won't be oxidized. So the choice is between bromide ions and water. And similar to the cathode reaction, it's the most positive oxidation potential that will occur. So this time, don't forget, we've got to look down our data sheet, we've got to basically reverse the sign of the E0 values, and we've got to look for bromide and water. And one of the tricks here is that bromide actually appears twice. Bromide ions can be oxidized to produce bromine liquid, or they can be oxidized to produce aqueous bromine, or in this case the water liquid could be oxidized as well. And looking down here, here are the oxidation potentials. These we had to reverse the sign of the sheet because these are oxidation reactions rather than reduction reactions. And it's also anodes before cathodes. The one at the top is most likely to have the most positive oxidation potential. And looking down here, they're all negative values, but minus 1.08 is the most positive value here. So what's going to happen at our anode is the bromide ion is going to be oxidized to form bromine liquid. Now we can actually calculate the E0 of the whole cell if you wish. and that E0 of the cell is E0 oxidation plus E0 reduction. It's minus 1.91 volts, which means you need to supply greater than 1.91 volts, making sure the negative terminal is the cathode and the positive terminal is the anode. And if the question in the HSC sometimes is, how would you identify the cathode or how would you identify the anode? Well, obviously the cathode is the one you've attached the negative side of the supply to, but this is a chemistry paper, so they'll be asking you some chemical ways to identify the cathode and anode. And we said here at the cathode that water is going to be reduced, and we said that hydrogen gas and hydroxide ions will be produced. So there's a way you could test which one's the cathode. You could do the pop test, as you see bubbles of gas being produced at the cathode, or you could do an indicator test, and it should show that the electrolyte around the cathode should be turning basic because of the hydroxide ions. What will you see at the anode? We said that bromine liquid is going to be produced, so we'll see brown bromine liquid forming at the anode. So that's the steps you've got to go through to calculate or do a calculation for an electrolysis reaction. If we also had to write the cell equation, you'd have to add your reduction half equation to your oxidation half equation. Luckily, these have the same number of electrons on both sides, so you've just got to add them together. If they have different numbers of electrons, you've got to change the number of species to make sure electrons are the same before you add them together. Next example now, it's very similar. We've got inert electrodes. This time we're electrolyzing a different salt. This is aqueous sodium chloride, and the process is pretty much the same. First of all, the cathode, you ask yourself what species are actually there. We know platinum's not going to take part in the reaction. We know that chloride ions have already gained an electron. They're not going to gain any more electrons. So the next step is to think about, well, the most positive reduction potential is the one that's going to be reduced. Looking at our reduction potential list, there's our two values. Sodium ions being reduced, minus 2.71. Water being reduced, minus 0.83. Once again, water is the most positive reduction potential, so that's what's going to take place. Next, look at our anode again. We know anode's oxidation. The species we have at the anode are these ones. So what can actually be oxidized? Well, platinum's not going to be oxidized. Sodium ions have already lost an electron, not going to be oxidized any further, so we've got to choose between chlorine and water. Once again, the most positive oxidation potential, or anodes, one at the top, is going to be the anode reaction. And once again, like bromine, you've got to be very careful. There's two possible chloride reactions being oxidized, but as we can see here, this time it's the water. The oxidation of water has the highest or the most positive oxidation potential of minus 1.23 volts. So we're going to have water being reduced at the cathode and water being oxidized at the anode. The overall cell value is minus 2.06 volts by adding those two values together. And how would you identify chemically the anode and the cathode? Well, once again, at the cathode we're getting hydrogen gas being produced, which it says here. Therefore, you can use the pop test. Hydroxide ions being produced, and therefore you could test its basic with an indicator. At the anode, you're getting oxygen being produced. You could use the glowing splint test for oxygen. Also, hydrogen ions are being produced. Therefore, you do an indicator test to test if it's acidic. So by changing the electrolyte, we have changed the overall cell reaction. And the next example here is similar to example 2. We're still electrolyzing aqueous sodium chloride, but now we're using non-inert electrodes. We're going to look at the effect the electrodes have. These are copper electrodes this time, and copper is it's not an inert metal, so therefore it will undergo reaction. So first of all, once again, the cathode, what species can be reduced? We've got copper ions there now. Metals won't be reduced, so we can take that out. Chloride ions won't be reduced because they've already got a negative charge. So once again, the choice between sodium ions or water being reduced, the most positive reduction potential is going to take place. Here's our reduction potentials, and just like before, nothing's changed at the cathode. It's going to be the water being reduced at the cathode in this reaction. So changing the cathode metal has no impact on the electrolysis because the cathode metal is effectively being protected. This is just like in electrolytic protection or cathodic protection. Whatever you make the cathode is protected. So you can put whatever metal you like here and it won't undergo any reactions as long as you're supplying enough voltage to it. So let's look at the anode now. Once again, anode's oxidation. Here are the species at the anode. What can be oxidized? We know metals can be oxidized. Sodium ions won't be oxidized, though they're already positive. And so we've got to choose now between copper, chloride, and water. We've got more things to think about. So once again, the most positive oxidation potential is going to be the one that takes place. And looking at our list here, this time copper is now the most positive oxidation potential with its minus 0.34 volts. So that means, unlike before, we had platinum, we had a different reaction taking place. This time with a reactive electrode, it's actually the electrode itself being oxidized. So we can find the E0 value for this cell by adding those two values together, minus 0.83 and minus 0.34. What will we observe? Well, once again, the cathode, we produce hydrogen gas. You can do the pop test, hydroxide ions, you can test a basic. And we'd see at the anode, the copper itself will be oxidized, therefore the electrode might see a difference. We might see it dissolving away a little bit. And also the solution would turn slightly blue around the anode because of the copper ions in solution. But just be aware, when you're changing electrodes, only the electrode of the anode makes a difference. Okay, example 4 is very similar to the previous example and example 2 as well. Once again, electrolyzing sodium chloride. We've gone back to platinum or inert electrodes, but this time we've gone for a higher concentration, a very high concentration sodium chloride electrolyte. Now, at the cathode, nothing's changed. We've still got sodium ions. They will not be reduced if there's water there. The water will always be reduced in preference because it's got the most positive reduction potential. But at the anode, something can start changing. So I'll just cross these out so we know that there's certain things that won't be reduced and what won't be oxidized, or platinum won't be oxidized and sodium won't be oxidized. We've still got to choose between the chloride and the water, which one's going to be oxidized. But we know that the oxidation potentials and reduction potentials in our standard sheet are for 1 mole per litre. And if we start changing the concentration, make the concentration higher, now we're no longer going to 1 mole per litre. And changing concentration can actually change your E0 values. And as we change the concentration of chloride, as we increase the concentration of chloride, these values start becoming more positive. They become, as there's more chloride in solution, more than 1 mole per litre, it becomes more and more likely that chloride will be reduced as opposed to water. So eventually this value will creep up to 1.23 volts or minus 1.23 volts. Then we'll get both chlorine and water being oxidized. And eventually, once this value gets high enough, this oxidation potential will become higher than water's oxidation potential, and we'll just get chloride ions being oxidized to chlorine gas. So as we increase the concentration, first of all, as we saw before, we get oxygen gas being produced at the anode, then we get a mixture of chlorine gas and oxygen gas at the anode, till eventually at high enough concentrations, we'd just be getting chlorine gas being produced at the electrode. So once again, at the cathode, we just have to do the pop test or test as basic, but eventually at high concentrations, the chloride will be oxidized and we produce chlorine gas here. Now, how do you test for chlorine gas? We don't need to worry about in HSC, but it is a pale green gas, which is very toxic and corrosive. All right, our last example now. This time we're using platinum electrodes again, but this time we're using molten or liquid sodium chlorides. We're taking the water out of it altogether. So at the cathode, once again, what can be reduced? We know that platinum won't be reduced, chloride ions won't be reduced. And now, because we've got no water here, there's no possible other choices. There's only the sodium ions that will be reduced. And this is what Davy did in his experiments. When he actually, for the first time, separated these reactive metals, he did it from the molten salts. And that's because if you had any liquid there, the water would be reduced first. But if there's no water there, then the metal ions can actually be reduced. So in this case, we have the sodium actually being reduced to turn into solid sodium. So we'd see some silvery sodium being formed on the platinum cathode. At the anode, we have oxidation occurs. What species have we got? Well, we know the sodium won't be further oxidized. We know the platinum is not going to take part in reaction. So it's just the chloride ion that's going to be oxidized. And what are the possible reactions? Well, I've got two reactions here on the data sheet. There's two possible chlorine reactions. The chlorine to chlorine gas is the most positive, but even still, we can't have the chloride ion being oxidized to chlorine aqueous because there's no water there anyway. So the only possible reaction was chloride ions being oxidized to form chlorine gas. So the E0 value for this cell is quite high, 4.07 volts. But this is the one situation where you'd actually get both the metal cation and the non-metal anion both being respectively reduced and oxidized. And this is how Davy, as I said before, produced the first reactive metals by electrolyzing the molten salts, because that's the only way you get the metal ions being reduced. And that's the end of our video number 28. I hope that was useful in helping you do your electric cell calculations.